On a modern digital map, the area appears empty. No streets, no buildings, no name. Just a patch of terrain rendered in the same neutral tones as uninhabited land. And yet, until the late 1970s, a town stood there. People were born there, they paid taxes there, they buried their dead there. Then, quietly, the town stopped appearing on maps. Not after a disaster, not after a war, not even after abandonment. It vanished after a geological survey, and the reason had nothing to do with danger. The town was small by any standard. Inland. Economically modest. The kind of place that appeared on government maps simply because it existed, not because it mattered. Geological surveyors passed through towns like this all the time. In the 1970s, large-scale mapping projects were expanding across many countries. Governments wanted better data on mineral resources, groundwater, fault lines, and subsurface stability. These surveys were routine, technical, bureaucratic. Most produced reports that gathered dust in archives. This one didn't. According to internal records, a survey team drilled a series of core samples on land just outside the town's limits. The goal was standard stratigraphic analysis, confirming that local geology matched regional models already well established. It didn't. The cores showed layers that didn't belong together. Density readings suggested mass that gravitational measurements could not account for. Instruments were recalibrated. Samples were retested. The anomaly remained. In the margin of one report, a phrase appears: "Formation requires further study." That study never happened. At first, nothing changed on the surface. Life in the town continued. Children went to school. Businesses opened and closed. Census records from the period show a stable population. But behind the scenes, something shifted. Survey teams stopped returning. Regional geological maps were revised, not to highlight the anomaly but to smooth over it. Stratigraphic boundaries were redrawn. Explanatory notes became more generalized. Then came the administrative notices. Property owners were approached individually, not with urgency but with paperwork. Offers to purchase land at fair market value. Relocation assistance. Compensation framed as optional but final. Some residents accepted immediately, others hesitated. Those who asked questions received vague answers. Infrastructure upgrades, long-term development plans, environmental reassessment. Projects that, on paper, justified relocation. Projects that, in reality, never happened. By the early 1980s, the population had thinned dramatically. Houses stood empty. Roads were no longer maintained. Public services quietly withdrew. Yet no official declaration of closure was ever issued. No evacuation order, no condemnation notice, no emergency decree. The town simply unraveled. What makes this unraveling unusual is what happened next. When new geological maps were published, the town's name was gone. Not marked as abandoned. Not labeled as historical. Removed. Later editions of road atlases followed suit. Digital databases inherited the omission. Over time, the absence became normal. To anyone consulting a modern map, the town never existed. Maps are not passive records. They are decisions. What is labeled is acknowledged. What is omitted becomes irrelevant. Removing a town from a map does more than confuse travelers. It affects funding models, infrastructure planning, historical preservation, and legal recognition. Yet in this case, census data remained accessible. Property deeds remained valid. School records persisted. Only the spatial representation vanished, which raises an unsettling question. Why erase a place geographically while leaving its bureaucratic footprint intact? As investigators would later discover, The issue was not that the formation beneath the town was dangerous. It was that it was incompatible. Geologists rely on models that assume continuity. Layers form through known processes: sedimentation, compression, erosion, tectonic movement. The formation beneath the town violated those assumptions quietly but decisively. Density readings suggested mass where none should exist. Gravity surveys hinted at inconsistencies without corresponding structures. The anomaly did not fit known categories. And crucially, it was stable. This wasn't an active fault. It wasn't volatile. It wasn't moving. It simply existed. And that was the problem. In geology, as in all sciences, anomalies demand one of three responses: explain them, classify them, or isolate them. Explanation requires new theory. Classification requires new categories. Isolation is easier. Rather than challenge regional geological assumptions, which were used in countless other surveys, the anomaly was cordoned off conceptually. And because the town sat directly above it, the town became inconvenient. Not dangerous, inconvenient. Former residents described the relocation as polite but final. No threats, no force. Just an unspoken understanding that refusal was not an option. Some recall being asked to sign non-disclosure agreements. Others remember verbal assurances that it was better not to talk about it. Better for whom was never explained. When residents asked why the town was being removed from maps, the answer was bureaucratic. Administrative update. A phrase that means nothing and everything. By the end of the decade, the town was gone. Not destroyed, not preserved, erased. And yet, the anomaly beneath the land remains. It was never resolved, never published, never disproven. In the next part, we'll examine the geological data itself. What made this formation so resistant to classification? Why it threatened foundational assumptions in modern geology? And why explaining a rock formation turned out to be harder than explaining the disappearance of an entire town. Because sometimes, it's not the surface that matters. It's what lies beneath, and what acknowledging it would force us to reconsider. The town disappeared quietly, but the land beneath it did not. It remained unchanged, unmoving, and unresolved, waiting in archived reports that almost no one revisited. To understand why an entire community could be erased to avoid explaining a geological inconsistency, we have to look closer at the anomaly itself. Not as a mystery, but as a problem modern geology was never designed to handle. Geology is built on continuity. Rock layers tell stories that are slow, cumulative, and legible. Given enough data, most formations can be traced to known processes: sedimentation, volcanism, tectonic pressure, erosion. This is not guesswork. It is a system refined over centuries, validated across continents, which is why the core samples taken near the town caused such unease. According to internal survey notes, the samples showed stratigraphic layers that should not coexist. Dense material appeared above less compacted layers without signs of intrusion or faulting. Mineral composition suggested origins from different geological epochs, compressed into a configuration that defied regional history. More troubling were the measurements that followed. Gravity surveys conducted as a secondary check produced readings that did not align with the observed density. In simple terms, the mass suggested by the rock did not match the gravitational influence detected at the surface. This wasn't dramatic enough to signal danger, but it was precise enough to signal error. The question was, whose error? At first, surveyors assumed instrumentation failure. Gravimeters were recalibrated. Control readings were taken in adjacent areas. Results elsewhere were normal. Only this zone remained inconsistent. The next assumption was sampling contamination. New cores were drilled from slightly different locations. The pattern persisted. At that point, the anomaly crossed an invisible line. It could no longer be dismissed as technical noise, but it also could not be easily explained without challenging regional geological models that were used as references far beyond this town. To explain the formation locally would require admitting broader uncertainty globally, and that carried consequences. Geological surveys don't exist in isolation. They inform construction codes, insurance models, mining rights, groundwater access, and infrastructure planning. A single, unclassifiable formation isn't just an academic curiosity. It threatens consistency across systems that assume predictable subsurface behavior. If the anomaly were labeled hazardous, the response would have been straightforward. If it were labeled valuable, it would have attracted interest. But it was neither. It didn't move. It didn't react. It didn't promise resources. It simply contradicted expectations. And contradictions are expensive. Internal correspondence from the period, fragmentary, heavily procedural, suggests a deliberate slowing of inquiry. Phrases like pending reassessment, deferred analysis, and awaiting broader context appear repeatedly. But no broader context ever arrived. The formation was marked for future study and then quietly excluded from subsequent survey scopes. That exclusion mattered, because geological models are built statistically. Remove an outlier and the model stabilizes. Keep it, and uncertainty spreads. The town sat directly above that outlier, and over time, the town itself became the easiest variable to remove. From an institutional perspective, relocating residents was simpler than rewriting geology. People can be compensated, land can be purchased, maps can be revised, but theoretical frameworks, once challenged, require years of debate, revision, and reputational risk. Geology, like all sciences, is conservative by necessity. It progresses by refinement, not by destabilization. The anomaly threatened destabilization, not because it was catastrophic, but because it was inconveniently fundamental. Though no official conclusion was ever published, later independent reviews of the surviving data point to a disturbing possibility. The formation behaved as if it were geologically insulated. It did not integrate cleanly into surrounding strata. It did not reflect regional stress patterns. It did not align with known depositional histories. In other words, it appeared to obey its own rules. Not supernatural rules, just rules we don't use. This is where the issue of precedent emerges. If one stable, unclassifiable formation exists beneath a populated area, how many others might exist elsewhere? Unnoticed, unnamed, and unexamined. And what would that imply about the assumptions underlying modern geological mapping? Erasing a town avoids those questions. Once the area is depopulated and omitted from maps, it becomes statistically quiet. Fewer measurements, less scrutiny, no reason to revisit old data. The anomaly remains, but isolated, not hidden, just irrelevant. And irrelevance is the most effective form of disappearance. By the time satellite mapping and digital modeling became widespread, the land where the town once stood had already been normalized into surrounding datasets. Resolution was averaged, anomalies were smoothed. The formation was still there, but no longer obvious. In the next part, we'll examine the decision-making process that turned a scientific inconsistency into a geographic erasure, and why officials later admitted, off record, that the problem was never risk. It was precedent, because acknowledging one exception can force a system to question everything it thinks it understands. The land didn't force the town to disappear. People did, and they didn't act out of panic, urgency, or fear of catastrophe. They acted to protect something far more fragile. Assumptions. By the time the town was nearly empty, the geological anomaly beneath it had already been quietly reframed. Not explained, not disproven, reframed. In internal documents, the language shifted. Early descriptions emphasized inconsistency. Terms like non-conforming, anomalous, model-resistant. Later summaries replaced those words with vaguer phrasing. Localized irregularity, data limitation, resolution constraint. Nothing false was written, but something essential was removed. This is how institutions manage uncertainty without ever naming it. They soften it. Geological surveys don't just record land. They inform decisions far beyond science. Zoning laws, infrastructure investment, insurance risk, resource rights. If the land beneath the town could not be classified reliably, every downstream system built on geological confidence would inherit that uncertainty, and uncertainty spreads. If one formation resists classification, others must be re-examined. If others fail, regional models weaken. If models weaken, trust erodes. The problem was never that the formation was dangerous. The problem was that it worked too well without explanation. Former officials later described the period as one of administrative fatigue, not crisis. Fatigue. Meetings repeated the same conclusions. Instruments were precise, but interpretation stalled. There was no error to fix and no theory to apply. And without a path forward, the anomaly became an obstacle rather than a discovery. So the question shifted. Not, what is this? But how much attention should it receive? And attention, as it turned out, was optional. In institutional science, precedent matters more than exception. If the anomaly were acknowledged publicly, it would establish that geological models, considered robust and reliable, could contain stable blind spots. That admission wouldn't just affect one town. It would ripple outward. Past surveys might need reinterpretation. Legal frameworks based on subsurface certainty could be challenged. Claims of predictive reliability would weaken all for a formation that posed no immediate threat. From a risk management perspective, this was unacceptable. Not because the science was wrong, but because it was incomplete in a way that could not be easily repaired. So, a quiet choice was made. No declaration, no denial, no formal suppression. Instead, the anomaly was excluded from new survey scopes. The area received no high-resolution follow-up. The town was removed as a variable. Once people were gone, the site lost relevance. Without relevance, funding vanished. Without funding, questions stopped. This wasn't erasure by force, it was erasure by attrition. For the residents, the experience was disorienting. They weren't told they were in danger. They weren't told their land was unstable. They were told it was no longer strategic. That word appears repeatedly in later correspondence. Strategic. It implies intention without explanation. Several former residents recall being advised, informally, not to pursue the issue publicly. Not threatened, just cautioned. As if curiosity itself were impolite. When the town disappeared from maps, its absence rewrote memory. Future planners never saw it. Researchers never questioned its omission. Students never learned its name. Without a place on a map, a town loses historical gravity. And without gravity, it stops pulling questions toward itself. This is why map erasure is so powerful. It doesn't deny existence. It prevents inquiry. By the time digital mapping arrived, the town had already faded into archival noise, but the formation beneath it remained. Unchanged, unresolved, still violating expectations. In the next part, we'll examine what happened when later technologies, satellite gravity mapping, digital stratigraphy, and computer modeling should have rediscovered the anomaly, and why, despite unprecedented resolution, the problem didn't reappear. Not because it was gone, But because it had been successfully trained out of the system, by the time satellites began measuring the Earth with precision unimaginable in the 1970s, the mystery should have resurfaced. Gravity mapping, remote sensing, high-resolution digital stratigraphy. If something beneath the land truly defied classification, modern tools should have exposed it again. Instead, they revealed something more troubling. Nothing. The late 1990s and early 2000s marked a turning point in geological observation. Satellite-based gravimetry allowed scientists to detect minute variations in Earth's gravitational field. Digital elevation models could infer subsurface structures indirectly. Regional geology was no longer built solely from ground surveys. It was cross-validated from space. In theory, anomalies like the one beneath the vanished town should have stood out more clearly than ever. But when researchers later examined satellite datasets covering the region, they found no obvious irregularities. No spike, no void, no contradiction. At first glance, the land appeared geologically ordinary, which raised a disturbing question. How does an anomaly vanish not only from maps, but from measurements? The answer lies not in concealment, but in methodology. Modern geological models depend heavily on averaging. Satellite data does not see rock formations directly. It infers them statistically, by smoothing measurements across regions to reduce noise and increase confidence. This approach is powerful. It is also unforgiving to outliers. Localized inconsistencies are often treated as error unless reinforced by multiple independent data sets. And this is where the earlier erasure mattered, because once the town was removed, the area lost priority. No targeted surveys, no dense sampling, no follow-up cores. Without concentrated data, the anomaly became diluted. Not removed, normalized. Resolution is not a neutral setting. High-resolution mapping requires justification, funding, relevance, purpose. Areas without population, infrastructure, or economic interest are rarely surveyed in detail. The vanished town no longer qualified. From a planning perspective, it was empty land, so satellite models treated it accordingly. Low priority, low resolution, heavy averaging. The anomaly was still there, but buried beneath layers of statistical smoothing. In effect, the system learned to stop seeing it. This is the uncomfortable truth about modern measurement. Technology does not eliminate human decisions, it encodes them. The absence of focused data in one generation becomes assumed normality in the next. Models trained on incomplete inputs produce outputs that appear coherent, until someone asks the wrong question. And no one was asking questions about a place that officially no longer existed. Decades later, a small group of researchers attempted to reprocess regional gravity data using alternative assumptions. Instead of smoothing anomalies away, they amplified variance. The results were subtle, but revealing. In one configuration, the region corresponding to the former town displayed slight but persistent deviations, too consistent to be noise, too weak to trigger alerts. Not proof, but a residue, a statistical echo of something unresolved. The researchers did not publish their findings, not because they were blocked, but because they lacked context. Without historical awareness of the original survey, the deviations meant nothing. Data without narrative is invisible. At this point, the disappearance of the town had achieved its final function. It had removed the anomaly not from reality, but from interpretation. The land remained. The formation persisted, but the frameworks designed to detect it no longer recognized it as meaningful. This is how systems maintain coherence. They don't deny contradictions. They absorb them until they no longer register. This story is not unique. Modern science increasingly relies on inherited data sets. Models trained on past decisions guide future inquiry. When anomalies are excluded early, especially quietly, they don't disappear. They become blind spots, and blind spots compound. The town was erased to protect geological assumptions. Those assumptions were then encoded into tools that define what is observable today, which means the cost of erasure is still being paid, just invisibly. The land where the town once stood is still there, undeveloped, unmarked, geologically normal, but the formation beneath it has never been explained, only forgotten. In the final part, we'll confront what the anomaly most likely represents, not by speculation, but by elimination, and why acknowledging that conclusion would challenge not just geology, but the way modern science decides which questions are allowed to exist. Because sometimes the most powerful disappearance isn't physical, it's conceptual. Every mystery narrows eventually, not toward certainty, but toward a smaller, more uncomfortable set of explanations. By now, we know what the formation beneath the vanished town was not. It was not a surveying error. It was not an active hazard. It was not a resource deposit. It was not a transient anomaly. What remained was not an answer. It was a limit. When geologists later reviewed what little data survived, they approached the problem the only way science allows when explanation fails, by elimination. If the formation were sedimentary, it would conform to depositional logic. It didn't. If it were igneous, it would show intrusion signatures. It didn't. If it were tectonic, stress markers would align regionally. They didn't. If it were artificial, there would be evidence of disturbance. There wasn't. Each category failed quietly, technically, and that is what made the formation so destabilizing. It didn't contradict geology violently. It contradicted it politely. The most conservative conclusion, never published, never formalized, was also the most unsettling. The land appeared to contain a stable geological configuration that did not emerge from known historical processes, yet interacted normally with its surroundings. No radiation, no seismic instability, no chemical anomalies, just a structure that existed, outside expectation. That possibility is not sensational, but it is corrosive, because modern geology depends on the assumption that Earth's subsurface can be understood as the sum of known mechanisms operating over time. This formation suggested there may be exceptions, not errors. Exceptions. If one such exception exists, others may exist. Not everywhere, but anywhere. And if that's true, then geological certainty becomes probabilistic rather than foundational. That shift would affect risk models, infrastructure planning, resource forecasting, legal definitions of land stability. It would introduce ambiguity into systems designed to minimize it. The formation wasn't dangerous, but acknowledging it would have been. Removing the town removed the need to decide. With no population, the land required no explanation. With no explanation, the anomaly required no category. With no category, the model remained intact. This wasn't deception, it was triage. Institutions routinely choose which uncertainties to carry forward and which to set aside. This one was set aside, not buried, just left alone. But unresolved anomalies don't vanish. They accumulate. They become assumptions embedded in data sets. They shape models silently. They define what future researchers expect to see. The town's erasure didn't eliminate uncertainty. It displaced it into the foundations of how the land itself is understood. This is not a story about a hidden town, or secret geology, or suppressed science. It is a story about how knowledge systems defend coherence. Science advances by explanation, but it survives by containment. When something cannot be explained without destabilizing everything around it, containment becomes the rational choice, even if that choice leaves questions unanswered for decades. The town that vanished still exists in fragments, in deeds, in census tables, in the memories of people who once lived there. And beneath the land, the formation still exists too, unclassified, unchallenged, unchanged, not because it is unknowable, but because knowing it fully would force us to admit something uncomfortable. That even in sciences built on deep time and solid ground, there are features we detect, but quietly choose not to name, because naming them would change how we understand everything else.